Hello, welcome to Introduction to Artificial Intelligence System. Today we're going to learn the basics of optimization. Optimization is kind of a way to select a best element with regard to some criteria from set of available alternatives. It is an important tool in engineering problem solving and also decision science. So today we're going to learn several mathematical ways to represent some optimization problems and how to solve this problem. But at the same time, as people like us optimize all the way in our daily lives, and also nature also does optimization for like selection or something. Before talking about in detail, let me briefly explain some example of optimization where people optimize in their daily lives. Let's assume we are a lifeguard, and you are here to save. You are here in front of the sand and ocean. And there is a person who wants to be rescued in this position inside the ocean. So to save these people, you might need to select the way among among various routes from here to there. Of course, there could be a lot of route, but from these, you need to select the best way. So, which way could be the best way? Some people think that A should be the best way because it is the shortest way from here, from the lifeguard to the people. But I might say B would be the best way because the shortest way to swim. So although it's quite long compared to the route of A, it will save some time because I need to swim a small amount of length compared to the way of A. So in that case, I could save some time, so I can save people as soon as possible. So I think the B would be the best way. So I will select the way of B. So this includes some way of thinking where we need to optimize the way of this. So this is one of the example of optimization problem. And by keeping in mind the previous examples that I explained before, let's simplify or let's rewrite this optimization process. As we can see here, optimization process should involve the three components. Firstly, objective function should be properly decided, and decision variable or unknown should be included. And finally, there could be some proper constraints or not. And by taking the example of saving people, the objective function could be minimize time for saving. And to do that, a decision variable or unknown could be the best route or best path. So here, from this safeguard, from the lifeguard, and from the person who wants to be rescued, we need to find the proper optimized route that can minimize the time for saving. And here, in this example, there is no constraint. But let's think about the other case where some obstacle, or let's say some building is in here, between here, so we cannot go through this building. In that case, the route should be selected, like route should be selected from this way or from this way. So in that case, proper constraints should be considered properly. So in that case, we cannot select the way similar to the previous example of this B route because we cannot go through this building. So instead of this, we need to select the other way, and this will make some constraints. So to define some optimization process, you should involve these three key components. You should firstly select a proper objective function, and then you should select a decision variable, and depending on the problem, the constraint should be included or not. So let's keep in mind these three key components, which should be repeatedly used for the whole lecture. And the way to solve this optimization process is just solving. So the optimization procedure is the process of identifying the objective function, variable, and constraints for a given problem. So for any given problem, you should model these objective function, variable, and constraints. You should properly identify these key components. And once the model has been formulated, the optimization algorithm can be used to find its solutions. And based on that, let's see how we can formulate this optimization problem in mathematical model. In mathematical expression, we can express the optimization problem as follows. I guess many of you have already encountered these formulas where we can interpret these formula as minimizing fx for every x. And here there is some constraints that the optimization problem is subject to. Gix should be, like, for example, smaller or equal to 0, and for I is equal to 1 to m. So as you can see here, as I mentioned like this, we can say that x is equal to decision variable, right? Here the objective function should be fx. So our objective function is fx, and our objective function is minimizing fx for x. So here x should be the decision variable, and f should be the objective function. And there are some constraints here. So that such that a Gix should be smaller or equal to 0. So this could be some constraint. As I mentioned earlier, there could be some constraint, or there should not be constraint. Constraint is kind of an option. So from this, we can rewrite, or we can formulate this optimization model as a mathematical form. So in previous example, we have looked into the optimization problem of minimizing something. And what if we need to maximize instead of minimize something, maximize fx? As we already know about that, actually the maximizing problem and minimizing problem is actually basically they are equivalent, right? So minimizing fx is just simply equal to maximizing minus fx. So we can consider these minimization problem or maximization problem is basically the same. And similarly, for the constraints, we have for the conditions for smaller or equal to 0, it's just exactly the same for minus x is equal to larger than or equal to 0. And if you have some constraints for hx is equal to 0, then you should consider the both case that hx should be smaller or equal to 0 and hx should be larger or equal to 0. So by simultaneously satisfying these conditions, we can just make the equivalent system that hx is equal to 0. And as I mentioned earlier, the constraints are not essential process. So in sometimes it can be unconstrained condition, or in sometimes it can be constrained conditions. So as you can see here, this one is just simply an unconstrained case where objective function is minimizing fx for decision variable of x. And for this one is just simply unconstrained condition. And for the constrained condition, there are additional one line, like for example, which subject to gix is equal to or smaller than 0 and hix is equal to 0. So by adding additional sentence of subject to blah blah blah, we can make constraints. But both can be determined. Both can be used for depending on the problems. And in optimization, there are very important concepts of global optima and local optima. And as these words indicate, global optima means the solution of some point that is the solution from the all axes. So for example, this could be the global minimum because this one is smaller than any other point from other x. On the other hand, a local optima indicates the solution of the optimization problem, but this will hold in some regional range. So from here to here, we can say this one is the optimal point. But when we enlarge the range of these x, then we cannot say this one is the optimal solution, right? Because there are some other point that has the smaller values compared to this point. So in this case, this point could be the local optima, but this point we cannot say this one is the global solution. The problem is then how can we guarantee this point as a local? How can you say the local solution should be the global solution? And for that, we need to know about the concept of convex. Convex having a shape like the outside of a bowl, we can represent the convex like this. In Korean, we call it as 볼록한. So the convex function is a function that has its graph like this bowl-shaped. So in mathematical way, we can represent the convex function like this. So for any x and y, their function value between x and y point should be always smaller or equal to the linear interpolation between fx and fy. So these dot line represent linear interpolation, and as you can see here, these function values are always smaller or equal to these dashed line. So these are the mathematical way of representing convex function. And for any x and y, if this condition is satisfied, we call it as a convex function. And for these, and the advantage of these convex function is that the local minima is always the global solution. So these local minima, we can guarantee that this local solution is a global minima. And for the problem that has convex set, includes some point that could be convex. And for this case, as you can see here, this value is not smaller than the interpolation between this value. So actually this region is not convex. We call it as concave. And if the set includes some part of concave, we cannot say that this is a convex set. So in this case, we call it as a non-convex set. And for this non-convex set or non-convex function, we cannot guarantee the local solution is equal to a global solution. Yeah. So for convex optimization is an extremely powerful subset of all optimization problems. So let's say if the all optimization problem is like this, we can say convex problem, convex optimization, and for non-convex. Of course, most of part will charge for non-convex optimization problem, but anyway, if the problem is kind of a convex optimization, it is extremely powerful because in this case, all local solutions are global solutions. So we can guarantee that what we obtain for local solution is actually for the global solution. So for convex optimization, we can rewrite the problem as like this. So similar to other optimization process, the objective function and decision variable can be written as like this. But in this case, if there are some conditions like which is subject to x is x for the convex set, then we can see that from this condition where C is a convex set, then we can find the global solution. And by keeping in mind the concept of optimization and its mathematical expression, let's solve optimization problems. From now on, we will now just consider a convex problem. And here, let's first start with the unconstrained and one-dimensional case. And let's say for the optimization problem for finding the minimum point, to find the minimum point x star, we can look the derivative of the function f prime x, right? By calculating f prime x and find the location where f prime x is equal to 0, we can find the flat point where its derivative is equal to 0. And for this convex problem, this is guaranteed to be a global minimum, right? Because in this case, the problem is said to be a convex problem. And based on that, let's generalize this optimization problem for multivariate function. So here, x is not limited to one-dimensional, but it is expanded to n-dimensional. So x has x1 and x2, x3, blah blah, and xn. So similar to one-dimensional case, to solve this optimization problem, we need to calculate the gradient of f. So instead of getting the point where f prime x is equal to 0, we need to calculate the point where the gradient of f becomes 0. And here, for defined as above, gradient is an n-dimensional vector containing partial derivatives with respect to each dimension. So as we know about the gradients, gradient is just simply calculate its partial derivative with partial derivatives with respect to each variable. So for example, partial f, partial x1 should be the first component of the vector, and partial f, partial x2 would be the second component of the vector. And similarly, partial f, partial x1 would be the nth component of the gradient vector. So we know the simple mathematical expression of gradient, right? And for the variables with continuously differentiable f, this problem is converted to similar to the gradient, similar to a discrete case. We can simply rewrite this as a gradient of gradient x for fx star. And from now on, we're going to learn how to find the point where gradient is equal to 0. And the first case is getting a direct solution. And in this case, we are now able to analytically compute where gradient is equal to 0. In this case, it's kind of a lucky case because we are able to compute it analytically. So let's take an example like this. So let's say we have a function of fx is equal to like this. Then as you can see here, we have two variables like x1 and x2. So fx is a function of x1 and x2. That means a gradient of x, gradient fx has 2 by 1 matrix, which could be lambda partial f, partial x1, and partial f, partial x2, right? And we know how to calculate partial derivative. So let's first calculate the first case of partial f, partial x1. In this case, this would become 4x1, and this would become 0, and this would be x2, and this would be minus 6, and this would be 0. So by rewriting this, we are able to write the first law of this equation, which is equal to 4x1 plus x2 minus 6. And similarly, when we calculate partial f, partial x2, this becomes 0, and this becomes 2x2, and this becomes x1, and this becomes 0, this becomes minus 5. So by rewriting, we were able to rewrite this as 2x2 plus x1 minus 5. And to find the minimum solution, we need to set this should be equal to 0 vector. So by rewriting this one, you can see that this problem can be rewritten as a set of linear equation where ax is equal to b, right? Then here, a should be 4, 1, 1, 2, and x should be x1 and x2, and b is equal to 6, 5. And from that, we are now able to compute the solution where x is equal to a inverse times b, and we were able to analytically find the minimum solution. So in this case, this is very lucky case where we were able to obtain the point where gradient is equal to 0. Yeah, and we know that the systems of linear equation or linear equation that has a form of ax is equal to b can be represented by using a matrix form. And here, as a linear algebra, we know we are learning how to calculate gradients, right? And to calculate gradients, we need to calculate the derivatives. So for that, we should know that we should know how to calculate the derivatives of a matrix. So for that, let's see this table. So for this, for the matrix that has a form of Ax is equal to b, we should know how the matrix derivatives. So let's say we know for the function of y, it's partial to calculate the gradient, we should know the partial derivative, which is equal to partial y partial x. And for the function that has a form of y is equal to ax, its derivative has a form of A transpose. So let's take an example of like this. If the matrix has a form of AX like this, then we know that its result is like x1 plus 2x2. And when we calculate this when you calculate the gradient of this function value, we need to calculate partial f partial x1 and partial f partial x2, which is just nothing but 1, 2. So as you can see here, its derivative becomes A transpose. So from that, we now know the relation of the y, and its derivative form has A transpose. And similarly, for the case of this, for the second case, let's say we have x1 and x2, and we have X transpose, which means we have x1 and x2, and A vector is equal to 1, 2. Then similarly, in this case, we also have x1 plus 2x2, and by calculating its partial derivative, we now have the same form of A matrix. So in this case, by calculating its derivative, we were able to the same form of A. And similarly, you may find the way for this. And we know that this one is kind of a vector inner product, which is equal to just calculating the magnitude time magnitude times. So here we know that its derivative has the form of 2x. So similarly, there are some relation between the original y and its derivative. So you may memorize this table for your own good. Yeah, and based on this table, let's revisit the same problem that we have solved in previous slides. So here, the equation can be rewritten as like this. The first three term has a quadratic form, so this can be rewritten as like this quadratic form. And for the fourth and fifth term, this can be written as -6 minus 5 times x1 and x2, right? So the linear equation can be rewritten as like this. So as you can see here, the x1 has the term of x transpose ax plus ax bx term. So here, this one is equal to b, and this one is equal to a. So x transpose ax plus bx form. And we know that by using this table, the derivative of gradient of fx is just simply from that, which is equal to ax plus a transpose x plus this one is equal to B transpose, which is nothing but 2, 1, x1 and x2 plus exactly the same because they are this A has a symmetric matrix plus B transpose X is equal to -6 minus 5, which is equal to 4x1 plus x2 minus 6, 2x2 plus x1 minus 5, which is equal basically the same as the one that we obtained earlier. So this is just another expression to obtain the gradient by using a matrix derivative. So you may, if you memorize this form, then you may use this to calculate the gradient when it's written in matrix form. Yeah, so far we have looked into the way to find solution where gradient is equal to 0 analytically by finding a direct solution. However, in most cases, more commonly, the condition that the gradient equal to 0 will not have an analytical solution, and in this case, we need to find another way, which is called iterative methods. As the word iterative means, we need to find solutions repeatedly. So that means by knowing the mathematical meanings of gradients, the gradient points in the direction of steepest ascent for function f. So at some point, let's say from the starting point at x0, we need to calculate a gradient at this point. And if the gradient is positive, then we know that its value will increase in this regional range. So from that, if you want to find the minimum solution, you may change the direction to the minus x direction. Yeah, and by keeping this in mind, let's take a look in more detail to find the solution iteratively. We call this way as a descent direction. And this method motivates the gradient descent algorithm, which repeatedly takes steps in the direction of negative gradient. So let's say we know that the meaning of gradient indicates the steepest ascent direction. So to find the minimum point, we need to go to the direction to the negative gradients. So this is very simple idea. So let me rewrite this idea in mathematically. So this can be written like this. So the idea is you need to update x with the update value that represents x minus a negative gradient. So here alpha indicates some step size, which is positive value. So as we know that alpha is positive value, this amount of value represents some amount of negative gradients. So we can represent this in graphically like this. So let's say from the starting point x0, when you calculate the gradient at this point, it's positive. Let's say it's positive. In that case, we need to go to the direction to the left, right? So by updating x, the new x with this value, by updating new x with these value, you can find another step from like this. So by iteratively finding the value, you can find the minimum solution. And let's assume another case. you may start from the point x0, and when you calculate the gradient at this point, it could be a negative, right? That means you can go on, you may update the x value by changing its value to the right. So by updating x0 to some value with a negative gradient, you may obtain the smaller value, and by keeping updating these value, you will obtain the zero derivative, which is equal to the minimized solution. Yeah, so we call this algorithm as a gradient descent algorithm. By keeping updating this x value with a negative gradient, you will be able to obtain this optimal solution. So you will be able to reach to the optimal solution. The remaining problem is then how we can choose a proper value of alpha. In gradient descent optimization, we update x value minus alpha gradient x fx. So by knowing the by choosing proper value of alpha, and here we call this as a step size, we need to update new x value. And for the step size alpha, we call this also as a learning rate. So let's see some example of choosing proper value of step size. Let's assume that alpha is too small. In that case, your updating value will change very small size. So that's why we call this as a step size. So here, it will take really lots of time. So it will converge very slowly. So like for example, from here to here, it will take really long time. So you need really long time. And on the other hand, let's say if alpha is too big, then in this case you will update x value with really large step. So here it will change to here, so it will keep going. So it will overshoot, or even could be diverged. And so it is really important to choose a proper value of step size alpha. And there's very clever way to choose alpha. In this case, alpha is not a fixed value, but instead it changes over time. So at first, we will change from the big step size, and we will slowly reduce its alpha value so that we can simply find the solution proper way. So it's really important to choose proper step size alpha or also learning rate. And let's see where will we converge when we use iterative methods. As I mentioned earlier, the optimization problem can be divided into the convex problem and non-convex problem. And for the convex problem, we are guaranteed that any local minima is a global minima. So in this case, by just calculating gradients at some points, you will get some local minima, which is basically just equal to global minima. But in the case of non-convex problem, you may converge to some point, but and that could be the optimized solution, but that could be a local minima. So as we can see here, when you start from here, you will converge to here, and this value is the local solution, where it's the optimal solution in this regional range. However, on the other hand, when if you start from this x1 point, then it will somehow convert to this x star, which could be the global solution. So in this case, for the non-convex problem, the initial point is really important. So I might say, when you start from somewhere here or somewhere here, you will converge to this local minima. And when you start, if you start from here or somewhere in here, somewhere here or somewhere in here, you will converge to this local minima. So for a non-convex problem, multiple local minima may exist, and to obtain global solution, you need to randomize initialization, and you should do a multiple trial. So let's say you should start from here, and you should start from here, and you should start from here, and by comparing the optimized result, you will get a better solution by doing instead of by doing only one times. Based on the idea, let's expand the idea of gradient descent in high dimension. So far we have looked into the case where one-dimensional case, but it's basically the same for a high dimension. So the basic idea is just repeatedly updating x value with a negative gradients. So just like the one-dimensional case, where we can grammatically represent this problem in this plot, similar to the high dimension, the function value will be the function of value x1 and x2 or xn. Okay, so let me summarize the two methods of finding the optimized solution by finding the point where gradient is equal to 0. So the first way is getting an analytical solution, or also by using direct or exact solution. And the second way is a gradient descent approach, where we iteratively find the solution by computing gradient repeatedly. So for the problem where you can obtain, you are able to obtain analytical solution, of course, the direct solution is the best way to get solution. And for the case of the gradient descent optimization, it is very easy to implement, so it's very general and can be applied to any problem where you can obtain gradients. So we call this as a differentiable function. And the advantage of gradient descent optimization is it requires less memory and computations for stochastic methods. And of course, for this sentence, I'm going to talk about it later on more detail. So the gradient descent provides a general learning framework. So for any problem that you are able to calculate you have a differentiable loss function, you can implement gradient descent optimization. So it's very general learning framework. So it can be used for both classification and regression. And I guess you are already have heard about neural networks. And for training artificial neural network, the gradient descent is the basic, very key important factor. So we were gonna see in later on. So we have looked into the two ways of solving optimization problems, and actually for practically solving optimization problems, thankfully, luckily, the good news is people have already done all the hard work of developing numerical algorithms. So they developed some algorithms and tools, and a wide range of tools have been developed for computing a solution. So what we need to do is just learn the basics of gradient descent theory, and we use these optimization solver where people have already developed. So simply by downloading this optimization solver, you are able to implement this optimization. And as I mentioned briefly earlier, gradient descent will be keep used for neural networks or deep learning, and so this could be gradient descent would be the key concept for learning artificial intelligence. And for the gradient descent study for neural networks or deep learning, people have already developed some very important Python library like TensorFlow, PyTorch, Keras, and something like this. So by using these library, we will be able to use these optimization solver, and I'm gonna keep talking about this in the offline lecture. And before ending, let me briefly explain the way to implement gradient descent in Python. Let's say for given this optimization process, the idea is just using update this value by using gradient descent methods. So for that, you can simply implement this code in here, like for I in range of 25, which means you're gonna do 25 iterative process. And for that, for given alpha, in this case, you need to set proper alpha value. You need to update like this. So by doing this step for 25 times, you're gonna able to obtain this value, which is just basically the same for this solution, where you will be able to obtain it analytically. So yeah, so that's what we have learned today. So today we have learned the basics of optimization, and we're gonna implement this gradient descent algorithm in Python in more detail in our offline lecture. Yeah, that's it for today, and thanks for your listening.